In this video, we're going to look at the moon and the inner solar system. And you're going to see that the moon bears an awful lot of similarities with the planet Mercury, so it kind of makes sense to lump them in together. Now, what do we mean by the inner solar system? We're talking Mercury, Venus. We're going to study the moon because we already talked about the Earth in a previous video, and Mars, the inner rocky bodies of the solar system. So what we see, if we look at this picture of the solar system, now the spacing is not to scale. However, it still gives us an idea that there's a dividing line. The inner planets, Mercury, Venus, Earth, Mars, all have solid surfaces. Now, some of the conditions are pretty rough, but theoretically, we could land on them and astronauts could walk around, or we could send a robot rover to walk around. So these are the terrestrial planets, the Earth-like planets, or the rocky planets. And they're pretty dense. They have densities of about 4 to 5 grams per cubic centimeter. And they tend to have a lot of metals. As you get further out, Jupiter, Saturn, Uranus, and Neptune, these are the gas planets, sometimes also called the giant planets. And look at their densities. Instead of 4 to 5, their densities are 0.7 to 1.5. They do not have a solid surface. You could never land on Jupiter. Now, there were older science fiction stories and older science fiction and superhero comic books, and they would have, aliens from Saturn or aliens from Jupiter. But that couldn't happen because there's no solid surface. Now, they do, as we think, have very dense cores, but there's nowhere to stand. So in this chapter, we're going to focus on the moon, Mercury, Venus, and Mars. So there's our moon. And let's look at some general properties. The moon is much lighter than the Earth. In fact, its mass is only 1/80th of the Earth. Gravity is about 1/6. So even though it's a lot less massive, it's also a lot smaller. It has a smaller radius. So if you remember the law of universal gravitation, the mass of the moon is much less, but so is the radius, so it kind of evens out a little bit. So it's about 1/6 of the Earth's gravity. And you may have seen this if you've ever seen pictures of when the astronauts were on the moon. They almost kind of hop in their spacesuits, almost like a bunny, like a rabbit. They're hopping. That's because they can, because it's only 1/6. They're not getting pulled down as heavily. The moon has no atmosphere. Now, that's not to say that it didn't have an atmosphere in the past. However, because the moon has such a low gravity, it was unable to hold on to its atmosphere. We think about the Earth's gravity holding us to the planet, but our gravity, luckily, is also holding in our atmosphere. It attracts the gas molecules and the atoms in our atmosphere, and the moon couldn't do that. Now, there's two pictures here. This one here is what we would call the light side, and we talked earlier that there really isn't a dark side. The dark side does get illuminated by the sun, but the light side is the only side that we see. It's the side that faces the Earth, because the moon's rotation and its orbit are such that it always shows the same side. And we've been to the moon from 1969 to 1972, so just 3 short years in all of human history. The missions Apollo 11 to Apollo 17. Now, if we look at the moon here, let me just point out a couple things that we're going to see in later slides. If you see the light areas, those are the highlands. Those are the mountains of the moon. And you can see on the what we call the dark side, or the back side of the moon, it's almost all that light color, the highlands, and it's very heavily cratered. Here is what we call the mare or the maria. And what that means is the seas, because they kind of look like the oceans on Earth. They're the darker spots, and they're not as heavily cratered. And we'll talk about why in just a minute. Those dark spots are what we sometimes call the man in the moon, because I guess some people can kind of see a face or a skull-like face there. Some cultures see it as a rabbit in the moon. So I guess it's sort of like when you see clouds and everybody sees something a little bit different. Now, the composition of the moon actually tells us a little bit about it. It's very similar to Earth, but not identical. And we know this because we've brought back, in the different Apollo missions, different soil samples. It's silicate rocks. Now, you might say, well, what's that? Silicate is a lot of silicon. And probably the most common silicate we know on Earth is sand. So sand and quartz, that's what the moon is made out of from its surface. It has a fairly low density compared to Earth, only 3.3 grams per cubic centimeter, whereas Earth is closer to 4 or 5. So we don't think there are a lot of metals to be found. I'm saying no. I guess you can't 100% say no, but very few metals. And there's no volatiles. There's no gases. It lost its atmosphere, many, many millions of years ago. An interesting question, and this is one that we've only solved in the last decade or so, is there any water on the moon? And the answer is yes. Some is chemically bound in the rocks. So that doesn't mean you can take the soil and grind it up and squeeze water out of it the way you would if you squeeze a washcloth or a wet towel. But we could probably get that water out of the rocks if we needed to. And surprisingly, in 2009, we found ice in some of the craters at the poles. And what we're looking at here are the poles. And those light blue spots are where ice is hiding. So those spots, and you might wonder, well, why only at the poles? They're permanently in shadow. They're permanently below the freezing point of water. And that water's been there for millions of years. It's also kind of neat the way we discovered it. What they did was they intentionally crashed this L-Cross satellite or L-Cross lander into the moon. And it threw up a lot of dust. The same way if you threw a rock into a sand pit, or on a beach, you might throw up some of the sand. Well, this threw up enough that we were able to determine that it was water. And this was in 2009. And let's say we want to go to Mars. Hydrogen and oxygen could be a fuel. So we might be able to take some of this water from the moon and use it as fuel later for a trip to Mars, either by people or by a unmanned craft. So we said there's two main areas of the moon, or two main types of terrain that we see. We see the highlands. Now, these are more rounded mountains. They're not sharp like the Rocky Mountains in the United States or the Cascades. They're much more gentle and rounded, but they're heavily cratered. The reason they're heavily cratered is because the moon has no atmosphere. So on the Earth, we have a pretty thick atmosphere. Most fairly small meteorites burn up on the way in. The moon has no such atmosphere. So there's nothing to stop any kind of rocks from space, any meteors or meteorites, from hitting it and cratering it. And we even have maps of all these craters, and scientists can study this to try and get an idea of the age of the different parts of the surface. And about 83% is cratered highlands or rocky areas. Now, the maria, or the seas, they're not heavily cratered. And as I said, those are the darker spots. And you can see these just with binoculars. Just if you have binoculars and you look at the moon, don't look at the sun ever with them, but you can look at the moon. It's totally safe. You can see the dark spots. And that's what we call the man in the moon or the rabbit in the moon. And they're not as heavily cratered. And I think you can see that in this picture. See how there's not a lot of craters here? If you look at the highlands here, all kind of craters. Now, what does that tell us? It tells us that they're younger than the highlands. Maybe they're about 3 billion years old or 3 billion years ago. So they're younger because lava flowed out and the lava was smooth. So there hasn't been as much time for these seas or the lowlands to pick up as many craters. Now, there have been collisions, but not as many as the older highlands, and that's about 17% of the moon. So where did the moon come from? Well, the current accepted model, or the most likely model, is the giant impact hypothesis. Some people call it the big splash. What we find is that the moon's composition is really, really similar to the Earth's crust and mantle. Very, very similar. So similar that it's suggesting a common origin. So what may have happened is, as these planets were forming, as all our planets were forming in the early solar system, a body the size of Mars may have hit the Earth. And basically, so if we look at the surface, or we look at the Earth, we have a lot of metals in the core, and then a lot of silicates, sand and stuff, and quartz above that in the mantle and the crust. Well, when this thing hit, it basically broke off part of the outer mantle, which is mostly the silicates, and that's the moon. And the metals stayed in our core, most of them. So that, and it's a computer model. I should say that. You know, we don't really have any way of going back in time and saying 100% this is what it is. But, you know, like any model in science, if it seems to really explain things and explains things better than some other models, we accept it. Another model is, well, maybe it was captured. But if it was captured, there's no real reason that that it wouldn't have many metals, and there's no real reason that its crust would have to have the same, very similar makeup to that of Earth. So the thought right now is that perhaps it broke off from the Earth early in the solar system. Now let's move inward. So here's our sun. We have Mercury right really close to the sun, and Venus, Earth, and Mars, just to remind you of the order. Now, Mercury is really good to study alongside this of the moon, and many astronomy books link them together. It's closest to the sun. Its year is only 88 days. Because it's so close to the sun, it's very difficult to see. It sets almost right with the same time as the sun does. And it's really the smallest official planet. It's only an 18th the size of the Earth. So it's a really, really small planet. It's unusual in that it has a very large metal core. And the silicates, remember we were talking about those silicates in the moon? It all fits together. The silicate layer is relatively thin. It does have a magnetic field, which suggests that this metal core is still molten, but it seems to be geologically dead. Now, what does that mean? Geologically dead is, as far as we know, there are no active volcanoes or lava or plate tectonics. It's not doing very much other than sitting there. It spins very slowly. One day on Mercury is 59 of our days. But it has very, very extreme temperature changes. During the day, there's no way we could live on Mercury, because it goes up to 430 degrees Celsius. And at night, when it's not facing the sun, it's negative 170. And it has such wild swings because it has no atmosphere. That's a 600-degree difference between night and day. That's the largest of any planet in the solar system. Now, if I showed you this picture here, now this is Mercury, but if I showed you or many people this picture here, they'd say, well, that's the moon. It looks a lot like the moon. It's very similar. It has no atmosphere, so there's nothing to slow down those meteorites or to burn them up, and it's become very heavily cratered over these many, many years. An interesting question is, well, why does it have such a large metal core? It's kind of similar to the way we think the moon formed. We think there may have been a huge impact in the early solar system, and it blasted away the silicates, leaving the metal core. In fact, because it's kind of dense, its gravity is about 38% of Earth. So if you could imagine, if you have an orange, and the center is the the part of the orange that we eat, and then the rind around it, the skin of the orange. So if there was a collision and it blasted most of the skin of the orange away, you'd be left with much more percentage-wise of the fruit, the inside of the orange. So that's kind of a way to think about Mercury. So let's move out to Venus. Venus is sometimes called Earth's twin. It's a lot like Earth, and we're going to see that in a minute. It has phases like the moon. We don't always see Venus full on. Sometimes we see a crescent or a gibbous Venus. And that told Galileo, just to remind you from a previous video, that Venus was probably orbiting the sun and not the Earth to see those phases. It's hard to see Venus. It reflects 80% of the sunlight because it has dense clouds, as I think you can see over here in the picture. Very, very dense clouds. So it's almost impossible for us to study the surface of Venus with a telescope. We would need to send something to orbit Venus or even a lander, and the Russians sent a lander many years ago. So we say Venus is a lot like Earth. It is and it isn't. Its day is 243 Earth days. Venus spins very, very slowly. And in fact, its spin is what we call retrograde. It's opposite. We spin west to east. Venus spins east to west. It's a slow planet, and it spins in the wrong direction. So, just as we've seen with the moon, just as we've seen with Mercury, there was probably a collision with the Venus probably hit something really big early in its existence, and that changed its motion, changed its rotation. Its year is a little shorter than Earth's, 225 days, and in fact, its day is longer than a year. So till 1 year, till it goes around the sun for 1 year, it hasn't even turned one day. It hasn't even seen one sunset yet. It's sometimes called Earth's sister planet because it's about 82% the same mass as Earth, and its gravity is 91% of Earth. So it's kind of a shame that the surface is inhospitable because it's pretty close to the same conditions that we're used to. Here's why I say the atmosphere is not hospitable or not really good for life. It's 850 degrees Fahrenheit on the surface of Venus. The atmosphere is 100 times denser than Earth, and it's almost all CO2. It's 96% carbon dioxide. Now, carbon dioxide is what we call a greenhouse gas. It's a gas that traps the heat. So Venus gets hit with sunlight, but its atmosphere is so thick that the CO2 acts kind of like a blanket, and the heat can't get out. So it just stays there. And this is sometimes called the runaway greenhouse effect. So what do we know? It's a little different than the moon in that it has more lowland lava plains. About 75% is kind of like the lunar Maria, where it's not heavily cratered and it's pretty smooth. It has two mountainous continents that make up about 25% the rest of the planet, similar to the lunar highlands, and they're named Aphrodite and Ishtar. So Venus was a Greek goddess. Venus is the Roman name for it. Aphrodite was the Greek name for that goddess, and Ishtar was another goddess from the ancient world. Now, this picture at the top was the Russian lander, and it landed. It wasn't a rover, so it only got a few pictures, and it was so hot that it sent a few pictures back, and it probably melted at this point, so it's probably just a heap of slag up there on Venus. Now, we've also sent some orbiters, and we do see craters. Because it's such a dense atmosphere, only very large objects, greater than 10 kilometers, can get through. And we think that it was geologically active, that there was lava, at least within the last 3 million years. And you can see here, there's a lot of cracks. That may indicate that this is still geologically active, that there are plate tectonics. In other words, that the crust is moving and splitting. It may still be volcanically active because you see these things here, they're not craters. We believe they're volcanoes. So we don't really know whether Venus is still volcanically active, whether there's still lava being produced on Venus. And then we're going to spend a little bit of time on Mars, and that'll be the end of the video. Mars is called the red planet. The reason it's red is because in the surface rocks, there's a lot of iron oxide, which we know as rust. And there's different forms of iron oxide. Kind of one of the most common ones is Fe2O3 that we learn in a chemistry class. So if you've seen rust, that's Fe2O3. Or if you're an artist and you've used the color burnt sienna, that's also Fe2O3. It's kind of a red brownish color. And it's the same compound that we believe is given the color to Mars. Now, interestingly, and you can see it here, Mars has polar ice caps, which maybe we could use those as a source of water if we ever sent a lander up there. And it has an axial tilt very similar to Earth. If you remember, Earth's tilt is about 23.5 degrees, and Mars is 25. So it's going to have seasons the same way that the Earth does. Mars has two moons, Phobos and Deimos, and you can see they don't really look like our moon. They do have some craters. They were hit by little other things different times in the past. But they do not look like our moon because they're not rounded. They kind of look like lumpy potatoes. They were probably asteroids that Mars's gravity captured. They almost certainly weren't formed alongside of Mars. We're almost certain that, an asteroid wandered a little too close and then Mars picked it up and put it into orbit. Well, a day on Mars, we would recognize it because it's 24 hours and 37 minutes. Just slightly longer. Now, its year is longer than ours. It's 1.88 years, and we could calculate that from Kepler's law, which we saw in a previous video. However, it's only 11% the mass of Earth, about a tenth of the mass of Earth. Because of its size, gravity is about 38% of Earth. And you can see here that we have the Mars Pathfinder, and it definitely has that reddish sky, and you can see some flatlands, and I think it's kind of neat that you can see the mountains here in the distance. And we've sent numerous rovers to Mars. So there's the little rover right there. I think it might be taking a sample. So could we land on Mars? Well, we could land there, but it's a very thin atmosphere. The atmosphere is almost entirely CO2, about 95% CO2, very similar to Venus. But it doesn't have that runaway greenhouse effect because it's only 0.7, less than 1% of the atmospheric pressure that Earth has. So it doesn't have enough atmosphere. It's very light. It's very similar to the moon. It can't hold on to the atmosphere. Again, we're seeing some of these same patterns. The highlands, the mountainous regions, are older and have more craters, and those tend to be in the northern hemisphere. The lowlands, much like the lunar Maria, are younger and have fewer craters, and they're volcanic plains. They don't have many craters because lava flowed more recently there and basically covered them up or smoothed them out. Now, there are volcanoes on Mars, and this is called the Tharsis region. Many volcanoes, we think most of them are inactive. The biggest volcano in the solar system is on Mars, and that's Olympus Mons, which really just means Mount Olympus. Mount Olympus was where the Greek gods were supposed to have lived. It's 3 times taller than Everest. However, it's spread out. So it's very, very tall, but it's spread out over 500 kilometers. Has very few craters on it. If you look here, there's very few spots where it looks like there's craters. So we don't know, is it still active? Does lava occasionally flow out of it, or has in the recent past? It seems to suggest at least it has in the recent past. Now, the question is, well, we know there's frozen water in on the ice caps. Was there ever liquid water? And the answer is yes. Percival Lowell was a very famous astronomer. And in fact, Pluto, he did not discover Pluto, but the first two letters PL are from Percival Lowell. So the suspicion is that that's why they called it Pluto. He thought that he could see through his telescope what he called canals, and even suggested there must have been intelligent life, and they dug these canals, to travel by riverboat. But once we got better telescopes and got better pictures, we could see, no, these were really random features. They didn't look like the way a canal would look on Earth. And one of the largest features on Mars, let me flip back a couple slides. You see this big scar here? Looks like a big scar. That's the Grand Canyon of Mars. I'll show you on this slide. There it is again. Or the Mariner Valleys. Now you might say, well, why is it valleys? Because there's different branches that branch off of it. It would run, if it were on the Earth, from Los Angeles to Washington, D.C. It's as long pretty much as the entire continental United States is wide. Probably caused by tectonic activity. Probably the crust was moving around here and kind of split open these valleys. However, our rovers have seen wind and water. They've seen gullies on Mars. So there is a strong suspicion that there was surface water on Mars at some point, and that it, because it left marks the same way we have sedimentary rock here on Earth, or we can see indications of the ridges in the valleys. And one last thing about Mars is the very famous face on Mars. There's a famous picture, and it's called The Face on Mars. And some people say that this is evidence that there was once intelligent life there on Mars. However, NASA says it's an artifact of the way the sunlight is hitting it. So if you look at the picture on the right, you can kind of see a face. But if you look at the picture on the left, if you look at the picture on the right, which is the exact same region at a different time of day, you can see, no, those are really just random lumpy features, and indeed they're not truly forming a face. You're welcome to make up your own mind about it, of course, as always, but that's what NASA's saying, that not really a face, it's just random features. And just like we like to see shapes in the cloud, or we like to make faces, we try to see faces in different drawings, that's probably what's going on.